planets form and come to be in their current orbits. That all being said, if we kind of go back to the theories that we came up with based on our own solar system, we can make some speculation about the Kepler-90 system. I mentioned earlier that the Kepler-90 planets seem to have this order where the big planets are further out. And in the solar system is taken as indication that planets like Jupiter and Saturn formed beyond what is called the snow line, can exist in ice form and help planets clump together. All of the Kepler-90 planets, though, are inside the snow line. So if you believe that they formed this way, then there must have been some way for them to migrate into where we see, possibly through their protoplanetary disk. But I'll go back to my caveat at the beginning. I don't think we really know enough how these planets form, especially given the huge dump of information that Kepler has given us in the last 9 years, to say for sure how we believe exoplanets in general form and migrate.
Okay, thanks.
Next we have Monica Young from Sky and Telescope.
Hi, this is Monica. Thanks for talking with us. I just was curious about what you had said earlier about the supervised learning. You said that you offered it training examples, and I was curious if you had any plans to ever make it unsupervised learning so that you don't offer it any labeled examples, which obviously take a lot of human input, and for further data sets that might not be possible. So I was just curious what your plans were for that.
Hi, yes, this is Chris. Thanks for your question. So to clarify what you said, yes. So where in this project we use a type of machine learning called supervised machine learning, which means we relied on a large set of data that had already been labeled. In other words, we already had the right answers, and we told our model what the correct answers were. There is another approach to machine learning called unsupervised learning, where you actually don't have the right answers. All you have is a large amount of data, and you turn a model to that data and ask it to learn things, even though you haven't specifically told it what the right answers are. This is an exciting type of machine learning as well. Obviously, it's great when you don't actually have a large labeled training set, and it's actually a very active area of machine learning research as well at the moment. I would say that most of the large successful applications of machine learning that you'll see actually have come about with supervised machine learning, and unsupervised machine learning is it's sort of not necessarily as clear cut how to apply it to a given problem. So I think it would be exciting to try and explore some unsupervised techniques on this data, but we don't have any specific plans at this time.
Okay, thanks. And if I can just ask a quick follow-up too, you mentioned that you had 96% accuracy for these planet detections. Can you just clarify if that was the false positives or false negatives, or what you were measuring there?
Yeah, so in this case, the 96% accuracy, we actually held out a small number of, it was actually 10% of the examples that had already been labeled by the human scientists, and we didn't show them to our model during training. And once it was finished training, we actually ran our model over that 10% of signals it had never seen before to see how it did. And the accuracy number in this case is simply the number of correct classifications, where a classification here is the classification, is this a planet or is this not a planet, just divided by the total number of things that it predicted.
Great, thank you.
Next we have Irene Klotz from Aviation Week.
Hi, thanks very much.
I have two quick questions. First is, are you all planning on publishing a paper about this? And the second question is, I think I heard the answer to this, but just to clarify, the difference between the technique you used to find the exoplanets this time, aside from hitting pay dirt, is that the software was modified to scan for weak signals, not strong ones. And is there any other difference between what changed in previous efforts to use neural networks to look for exoplanets? Thanks.
I can take a stab at that. So this is Andrew. Yes, we have published the paper. It's not published yet, but it has been accepted for publication. It'll be posted on the archive tonight, and a copy of the paper is available for download now. I believe it's in the press release, but maybe someone can confirm that for me.
Yes, the current link can be found in the press release.
Yeah. And the second question was asking about what the differences were between our search for planets and Kepler data using neural networks and other previous searches for planets and Kepler data using neural networks. Is that right?
Yes.
So one of the things that's interesting is that there haven't been very many searches for planets and Kepler data using neural networks. There have been a couple papers recently, maybe 2 or 3 papers recently, that have used neural networks to identify planets in simulated Kepler data, or which have shown that neural networks can identify previously known planets in Kepler data. But as far as we're aware, no one has conducted a search like this in Kepler data using neural networks. Does anyone else have anything to say about that?
This is Chris. Yeah, I think another part of the question, which I'll address, is about your question about the fact that we turned down the threshold of the search for candidate signals, and therefore we looked at the weaker signals. So just to clarify what we meant there, previous searches of the Kepler data would output the strongest signals, which are the most likely to be real planets, and then humans or other automated software would examine those to look to decide if they were new planets, if they were actual planets or not. In our search, we ran a similar search for signals, for candidate signals, and yes, we actually focused on the weaker signals, and then what we did was we actually applied our neural network model to those weaker signals to basically ask it which of these weak signals are the most likely to be planets. So that's the key difference with this work.
Thanks. And Chris, are there any other people at Google that are doing astronomy projects like this?
There's actually a large number of other science efforts at Google to use machine learning in science. I'm not specifically aware of any other Google efforts in astronomy specifically. But I am aware of other efforts to use neural networks, for example, to predict the properties of molecules, to detect diabetic eye disease. But I'm not specifically aware of any other astronomy projects at Google. But it's a large place, and so there very may well be some.
Thank you. Thanks. Next we have Cesar Baima from Global Newspaper Brazil.
Hello, thank you for taking my question. I would like to know first if this kind of machine learning and artificial intelligence will or could be used on the test data for the search of Earth-like planets, and how it would bring us closer to find the true Earth twin that is on the orbit of some star and on the habitable zone.
This is Chris. So I might take a stab at the first part of this question where you asked about whether this type of machine learning will be able to be applied to the TESS mission.
Yeah.
So so one thing you'll recall about this work is that sort of the key ingredient was these 15,000 signals that had already been examined and labeled by human scientists. And so when the TESS mission launches, we won't actually have a set of previously known and identified signals. So there are two ways, I think, in which we will be able to apply this same sort of technique to the TESS mission. One approach is perhaps we could just wait a little while until some humans have actually labeled enough test signals in order for us to train a machine learning model based on the human classifications. But another perhaps more exciting area of research, but a bit more exploratory, is whether we can perhaps simulate some signals, for example, from the test mission, and then use those simulated signals to train the machine learning model, and then apply that machine learning model to the real signals. But that's a little bit more exploratory, and it may be a bit difficult to get that to work.
So this is Andrew. Your second half of your question was asking if this will help us find Earth-sized planets in Earth-like orbits around sun-like stars. Is that right?
Yeah.
Yeah, so I think that's plausible. So one of the reasons that these Earth-like planets around sun-like stars in these long-period orbits are rare is that they're just really hard to find. They're right at the edge of what Kepler can actually detect. So we're hoping that if we use this kind of strategy of looking for the weaker signals and using machine learning to separate out the false positives from the real planets, we can boost Kepler sensitivity just a little bit more and hopefully be able to start finding these extremely interesting and exciting planets.
Okay, thank you.
And with that, we've got time for 3 more questions. We're going to take questions from the Business Insider, Popular Science Magazine, and then the New York Times. Let's go ahead with Dave Mosher from Business Insider.
Thank you for taking another question. I want to try to cram in just a couple more here. Is there a catchy name or a simple name for this machine learning model other than that? Do you guys have a nickname for it? Should we call it the cats and dogs model? That's question number one. And then I guess the other question is, help me understand, there's a lot of other Kepler data, K2 data that remains. How many more targets are you going to look at, and how many planets do you expect to find based on what you've found in this initial run? And then if I have time for a third, I'll do that.
Hi, this is Chris. So for the first part of your question, no, we actually don't have a catchy name. So perhaps that's up to someone to suggest a good one for us. In terms of targets to look at, we have concrete plans to look at the remainder of the data set from the main Kepler mission, which is at least 150,000 more stars. In terms of how many more planets we expect to find, I wouldn't really want to speculate there because I don't know. One of the things which we did in this project was we searched for new planets around stars which are already known to host transiting planets, and therefore we know that the star already hosts planets where the orbits are aligned in such a way that the Kepler telescope can detect them. So when we turn our machine learning model to new stars, which may in fact have planets, there's probably going to be a lot of those whose orbits are not inclined such that the Kepler telescope can detect those. So I'm not sure exactly how many new planets we expect to find, but I certainly hope to find some more. And perhaps I can let Andrew add anything else.
Yeah. So it's hard to guess how many new planets we'll find, partially because if we find them, they're going to be in a new regime. They're going to be the smallest planets, and they're going to be the longest period planets. And if you go into a new regime, it's always dangerous to predict how many planets you're going to find because you just don't know. You've never looked before. So that's why we're doing it. We want to find out.
Okay, let's go to Robert Berger from Popular Science Magazine.
Hi, everyone. I'll make this quick and easy for you. I think I already know the answer to this, but is this the first time, to your knowledge, that an artificial intelligence system like a neural network has successfully discovered exoplanets?
So this is Jessie. I'll start with this, and then Chris and Andrew can correct me if I'm incorrect. So machine learning and artificial intelligence is a pretty darn broad category, and certainly versions of machine learning have been used to help us assess whether or not a signal is due to an exoplanet before. What this is the first, and this is the first time that, as far as we've been able to figure out, that a neural network has been used to successfully identify a planet. And neural networks are just really powerful algorithms, and it's really exciting to see it applied to this data set.
Yes, this is Chris. I believe, yes, I also believe, as Jessie said, that this is the first time that a neural network specifically has been used to identify a new exoplanet. And the other sort of first about this is that I believe we're the first to actually take a neural network and use it to explore this sort of new regime of data, this sort of weaker area, these weaker signals. And this presents a really great opportunity because there's going to be lots more weaker signals for us to look at when we actually turn to the full Kepler data set.
This is Andrew. Yeah, I agree with pretty much everything that's been said. I do want to call out, though, the discovery of LHS 1140b, which was discovered by Jason Dittman using the MERTH telescope. He was assisted by a neural network which identified which transits detected from the ground may or may not have been contaminated by bad weather and were false positives. So it's a complementary type of approach which has been used to help discover planets, but it's fundamentally a little bit different than what we're doing here.
Thanks so much.
Okay, last question. We have Nicholas from the New York Times.
Thank you so much. The last question just sparked a quick question in my head, but I have two here. First one being, can you just give us one more time a simple layman's definition of what you mean when you say neural network? That's one. And then two, when we're talking about Kepler 90 and how it's 8 planets are all kind of scrunched together and how this is much different from our solar system, is it so much that the planets in that solar system are scrunched together, or is it that our technology can only see the planets that are really close to their sun that are scrunched together? So it might not be that out of the ordinary. Thank you.
Hi, this is Chris. So I'll take the first part of that question, and I'll try and describe a neural network in as few sentences as possible. So the way I would say a neural network is a machine learning algorithm that is very loosely inspired by the human brain, and it has a variety of uses, but let's focus on the fact that it can be used to classify inputs. So in this case, so we already talked about the question of classifying images of cats and dogs, or images of trucks and cars, or anything like that, or in this case, classifying signals from the Kepler telescope as being planets or not planets. So it's a type of algorithm that can actually classify inputs, and how it does that is it actually learns by example. So we're actually going to train this model by giving it a large set of labeled examples and allowing the neural network to actually learn which patterns in the input will it use to make the decision to classify the input as one category or another?
This is Andrew. I'll jump in for the second part of that question, which was about whether Kepler-90 is really that unusual, or is it just this is what we're able to see? And I think that's a really great question. When I think about what we know, it's very little. We have really complete understanding of just one planetary system, and that's our own solar system. And when we start asking questions like, what are the how does the solar system stack up to other planetary systems, we have to remember that we only have incomplete views. So we search for planets with transits a lot. That's how Kepler searches for planets. And as you said, transits are really mostly sensitive to close-in planets. We can search for planets by gravitational microlensing. Microlensing is sensitive to planets further away from their stars. Eventually, we'll be able to search for small planets using direct imaging, directly taking pictures of planets by separating the light from the planets from the lights of their stars. And all of these techniques will give us different views of planetary systems. And I think only when we combine those techniques together, we can get full views of exoplanet systems and start to put our own solar system into context and ask how common are 8 planet systems like our solar system with orbital spacings this far apart typically compared to the tightly packed systems like Kepler-90 or some of the really, really distant systems like the directly imaged planets around HR 8799.
Mm-hmm. So we just don't know yet.
Yeah, I would say that it's too early to say, and that's one of the most exciting things that will come out of the next few decades is we will get the technology and the missions to start looking for planets in these additional ways.
Mm-hmm. Great. Thank you.
And that's what we have for today's News Telecon. I'd like to thank the panelists and our operator for their time today. I'd like to ask the panelists to stay on the line for a few minutes for a post follow-up. If you joined this telecon late, you can listen to it again with the information that is on our press briefing site. To find out more about these findings or for more information on any of NASA's many programs and projects, visit us at the web at www.nasa.gov or via our many social media venues such as Facebook, Google+, Twitter, and YouTube. Again, we are holding a Reddit AMA Ask Me Anything on today's announcement at 3 p.m. Eastern, so please go to the subreddit Science for more information. Thanks for joining us and have a great day.
At this time, now we conclude today's conference. You may disconnect, and thank you for your attendance.